So now we get to the meat of why we talked about signal space. It's a fundamental concept, but the place where it comes up most often is in what's called passband and multiple access. So let's introduce that today. And I'll have plenty more to say about this next. Okay, so so far, all the signals we've talked about have been what are called baseband. And basically what baseband means is centered around, the Fourier transform is centered around 0. So in other words, if you take one of our signals, let's say the polar NRZ signal, and you take the the discrete time Fourier transform of that and plot it, you will probably get something like this, centered around 0. So now we're going to look at the case where that's not possible anymore. So passband, where passband occurs is where the Fourier transform is centered away from 0. So in other words, we would take this, and in the Fourier transform domain, we would center it about somewhere else, like this. So we would take that and plot it somewhere else in the frequency domain. So strictly speaking, I'm not sure if centered is the right terminology. I hope you get what I mean by that. But I mean, strictly speaking, there would be an image of that Fourier transform in negative frequency. But basically, I mean, this sort of the information-bearing content of the Fourier transform is centered around somewhere other than 0. So why would you do this? There's a whole lot of reasons. One is, so let's say I'm connected by a wire to you, so there's no real problem with sending a baseband signal down the wire unless more than one person wants to use the wire. So for instance, we could agree that you get to use baseband and I get to use some chunk other than baseband. In another example is this: in the traditional phone system, it was impossible to send a DC signal. So, in fact, there was some knockout band down here where you couldn't transmit a signal. So, you could not transmit a signal of this kind. They had to be pushed up just a little bit in frequency domain, so that there was no DC component to those signals. Can anyone think of another example where this would be useful? Yes.
Getting rid of noise.
Getting rid of noise, that's interesting.
60 hertz or something.
So that's a good one. So at 60 hertz, there's often a power component, so you might want to avoid that just by shifting up slightly. But I also heard mobiles over here, and that's a key one. So wireless is one of the key applications of passband. So let's break down some examples. The two takeaway examples that I want you to think about are actually there's three that we talked about. Multiple access. Another one would be spectrum shaping. So that's where we start talking about you can't send a component to DC, you want to avoid 60 hertz, that kind of thing, and wireless. So this is the key one. You cannot send, there's no such thing as a DC wireless signal. And in fact, if this is a low bandwidth, if this is fairly narrow in frequency domain, let's say this is -1 kilohertz to 1 kilohertz, it's really, really hard, actually. Even, it's impossible to send a DC signal over wireless. It's really, really hard to send a very low frequency signal over wireless. So if you think about, I mean, I'm sure you covered this in signals and systems, but if you think about something like the analog radio bands, FM, for example, everybody gets 200 kilohertz up in the 100 megahertz range. So let's call it 100 megahertz, or 100.2 megahertz. Actually, they're usually centered at odd decimals. So let's call it 99.9, 100.1, 100.3, and each of these is some independent station. So here, it's useful firstly because it's impossible to transmit at DC, and also for multiple access. So we can use the wireless spectrum to send many radio signals at once.
So when you say DC signal, you mean the baseband component, right?
Yes, I mean this. I mean, you can't send, if you take this, some constant, so that's a DC signal, right?
Oh.
And you send that to an antenna, nothing will happen. Because, actually, why won't anything happen? Did anyone take a electromagnetics course? So what's an EM wave? Basically, an EM wave is an oscillating electrical field, and orthogonal to that, an oscillating magnetic field. So if you have no oscillation, you got no EM wave. So there's no such thing as a DC wireless signal. The reason why, okay, so another point I should mention, the reason why everything is at least in the megahertz is that it's really hard to get an efficient antenna that works at, it's really hard to get an efficient antenna that's not at least a quarter of a wavelength long. So a quarter of a wavelength up in this domain, up at about 100 megahertz, is about a meter, I think. In the megahertz, it's about 100 meters, and that's why you see these huge radio towers that transmit like shortwave and AM. Up here, this is about the length of rabbit ears, so if you have an old TV or an old radio or something with a rabbit ear antenna, they're about yay long, and that's why. Up in the gigahertz, so factor of 10, you have about 1/10. Actually, it'd be more like where your cell phone operates is about 2 gigahertz. So there we go, a factor of 20 in frequency. So a factor of 1/20th in wavelength. So that's why your cell phone antenna is about yay long, because that's the most efficient. Anyway, I digress. So what we got to do is we got to take away, we got to take our baseband signals and somehow get them up here. Okay, so we need two things. Firstly, we need that the baseband is bandwidth limited. And secondly, we need a way of shifting signals in the frequency domain. In other words, we need a way of taking this baseband signal and shifting it in the frequency domain. So we're just taking that and sliding it along.